The general goal of the following experiment is to determine the overall shape of protein complexes. This is achieved by acquiring mass spectrometry ion mobility data for protein complex ions and measuring the drift time values of each charge state. As a second step, the experimental conditions are validated in order to ensure mobility measurements of native protein structures. Next, the measured drift time values are correlated with cross-sectional areas. Results determine the collision cross-section values of proteins or protein complexes with unknown three-dimensional structures. This information provides clues on their overall shape, subunit packing, and topology.
Hi, I'm Isaac Michaleski from the lab of Michal Sharon, Department of Biological Chemistry at the Weizmann Institute of Sciences.
And I'm Noam Kirschenbaum, also from the lab of Michal Sharon.
Today we will show a procedure of measurement to collision cross-section of protein complexes using hybrid mass spectrometry and ion mobility instruments.
We use this procedure in our laboratory to study the overall shape and quaternary organization of protein complexes.
So let's get started.
This procedure focuses on ion mobility-mass spectrometry or IMMS analysis of protein complexes. The sample preparation steps, instrument calibration, and MS and tandem MS optimization procedures are demonstrated in a related Jove protocol. In general, this protocol involves low micromolar concentrations of complex in a volatile buffer such as ammonium acetate. Given that 1 to 2 microliters are consumed per nanoflow capillary, prepare 10 to 20 microliters as a minimum volume to enable optimization of MS conditions. To begin this procedure, set the travelling wave or T-wave synapt IMMS to the following modes of operation. Mobility TOF, in which the tri-wave and pressures are automatically set for both IM and time of flight separation of ions, positive ion acquisition, and V mode, setting the path of ions through the flight tube and reflectron. Turn on all gases. Here nitrogen is used for IM separation and argon for the trap and transfer regions. Recommended initial values are a gas flow of 24 ml per minute for the IMS device and 1.5 ml per minute for the trap region. Next, set the mass to charge ratio acquisition range. For an unknown protein complex, use a wide mass range initially, which can then be reduced to the desired values. Adjust the MS profile accordingly for maximum transmission efficiency. For large complexes, the acquisition mass range should be set from 1000 to 32,000 mass to charge ratio and the MS profile to auto. Otherwise, the profile can be set according to the chart shown. Check the RF setting and, if necessary, adjust to values appropriate for large protein complexes, as shown. Next, load the sample. Apply capillary voltage and low nanoflow pressure. Once spray is initiated, try to reduce the nanoflow pressure to a minimal value. In addition, adjust the position of the capillary with respect to the cone. Adjust the MS acquisition parameters in order to acquire well-resolved MS spectrum. Optimize the pressure gradient along the instrument and the sampling cone, as well as the potential settings of the extraction cone, bias, trap and transfer, as detailed in the associated Jove protocol. Although these parameters are sample dependent, shown here are the conditions used for acquiring MS spectra of various ion masses, from peptide to protein complexes. Large ions require higher collision energies and bias voltage. It is also recommended to increase the back pressure for the analysis of large protein complexes. To minimize the activation of the complex, try to gradually reduce, in steps of about 10 volts, the sample cone, extraction cone, trap and bias voltages without changing the position of the peak. Once an optimum mass spectrum is obtained, the drift time or IM profile should be adjusted. When analyzing protein assemblies, optimal conditions for both mass and mobility measurements are often incompatible. Therefore, it is important to strike the proper balance between the two. Overall, the ion mobility plot should be optimized such that the peaks are distributed over the entire drift time range, and the peak profile is smooth, approaching a Gaussian distribution. Significant peak asymmetry can be related to poor separation of multiple conformations. T-wave velocity, T-wave height, and IMS gas flow rate can be tuned to optimize the mobility separation. Increasing the T-wave velocity widens the drift time distribution profile, while increased T-wave height values narrow it. Similarly, increasing the IMS gas flow starting at 10 ml per minute minimum shifts the drift time profile toward higher values. Work to optimize the ion mobility spectrum by fixing 2 of the 3 variables and optimizing the third. Set the T-wave velocity to 250 meters per second and the gas flow to 24 milliliters per minute. Then, as a starting point, set the T-wave height to 3 volts and in a stepwise manner increase it in 1 volt increments. When high bias voltages are used, it is recommended to reduce the IMS gas pressure and in this way enable the decrease in the bias voltage. As a consequence, complex activation and dissociation will be reduced. A rollover effect can appear when conditions are not optimized, observed as an identical peak in the first part of the drift time spectrum and the tailing edge. When the ions do not traverse through the IM device effectively, their journey may take longer than the time required for the next ion packet to be released into the mobility cell. As a result, a new bunch of ions is released from the trap region before the previous packet has been delivered to the pusher region. To eliminate this artifact, increase the T-wave height and decrease the T-wave velocity and IMS pressure. In addition, the trap release time can be adjusted. Moreover, it is important to validate that the transfer T-wave height is set to at least 5 volts. Also, to prevent leakage of ions towards the IMS cell, the mobility trap height should be kept at maximum levels. Low velocity and high amplitude of transfer T-waves may lead to the rippling of the drift time distribution profile. This artifact occurs when the mobility separation of ions is not maintained through the transfer and TOF regions due to partial synchronization between the pusher frequency and the transfer T-wave velocity. To eliminate this effect, either the pusher time or the transfer T-wave velocity should be adjusted. Since the pusher frequency is related to the mass range, this artifact may reappear when this parameter is changed. T-wave height exerts a minor effect, though its reduction may also help to eliminate ripples. Once the aforementioned parameters are optimized, the IM-MS data can be acquired. To achieve highly resolved MS peaks, protein complexes are often activated within the mass spectrometer to promote the stripping of residual water and buffer components. However, if the activation energy is increased beyond a threshold value, partial unfolding can occur, forming multiple intermediate states, which are unlikely to correspond to the native solution state structure. As a result, the drift time peak may be shifted and broadened, reflecting the heterogeneous population of unfolded structures. In order to obtain drift time data consistent with solution phase structures, it is essential to carefully control the voltages used for accelerating ions prior to IM separation. Therefore, increase capillary and cone voltage in a stepwise manner while monitoring the effect on the drift time spectrum. Moreover, for high MS resolution, it is preferable to increase the transfer rather than the trap voltage. The IM device is positioned first, followed by the transfer region and the TOF analyzer. Since the activation follows the IM measurement, the ions remain unaffected for IM, while the MS accuracy can be increased. To ensure that data acquisition is performed under conditions which maintain the native structure of the complex, it is important to collect data over a range of experimental and solution conditions, rather than adhere to a single optimized set of parameters. For that reason, increase the trap collision voltage in a stepwise manner, and acquire data at 10-volt intervals while monitoring the effect on the ion mobility profile. Finally, to identify the unfolded conformations and assess the acquired data, manually induce dissociation of the protein complex by titrating the sample with acetic acid over a pH range of 2 to 7 and record the data. Proceed to analyze the data. In the T-wave IMS system, the cross-sectional area is defined by a drift time calibration approach using calibrant proteins with known cross-section values. First, prepare denatured calibrant protein solutions at 10 micromolar each. use equine cytochrome C, horse heart myoglobin and bovine ubiquitin in 49-49-2 volume ratio, water methanol acetic acid. Next, acquire IMMS data for the calibrant proteins under exactly the same instrument conditions used for the target protein or protein complex. Keep all the voltages and pressure values identical to preserve the IM separation settings. After acquiring the data, extract the experimental drift time value for each charged state of the calibrant proteins. Correct each of the calibrant drift times T'(D) using the following equation, where m/z is the mass-to-charge ratio of the observed ion and c is the enhanced duty cycle (EDC) delay coefficient. Its value, typically between 1.4 and 1.6, is instrument dependent. The EDC value is indicated within the System 1 Acquisition Settings 1 Acquisition Setup tab. Correct each of the calibrant cross-sections for both ion charge state and reduced mass, where omega C is the corrected cross-section, omega is the literature cross-section, Z is the ion charge state, M is the molecular weight of the calibrant ion, and Mg is the molecular weight of the IM background gas, which is typically nitrogen. Plot the ln of T'(D) against the ln of omega C. The resulting curve corresponds to the following equation. The parameters x and a can be extracted by fitting the plot to a linear relationship. The slope x corresponds to the exponential proportion factor and a represents the fit determined constant. Calculate the fit correlation coefficient r². Acceptable values for r² are greater than 0.95. A lower correlation coefficient value may be due to incomplete unfolding of the protein calibrants, aging of the sample, dissimilar experimental conditions used for the different calibrant proteins, noisy spectrum, and incomplete processing of data or calculation error. Correct the calibrant drift time using the determined exponential factor x, and validate your calculations by replotting omega C versus T'(D). Define again the correlation coefficient. Higher values than 0.95 are to be expected. Similarly to the steps described before, correct the measured drift time of the target protein or protein complex, and calibrate the drift time of the target protein or protein complex using the calculated exponential factor x. Calculate omega of the target protein or protein complex using the fit determined constant A, where omega equals ATD. Repeat these steps for each experimental condition. When defining the cross-sectional area of the unknown protein or protein complex, we recommend that each experiment be repeated at least 3 times, and the standard deviation of these triplicate measurements determined. Once the collision cross-section values are determined, modelling approaches are employed in order to predict the topological arrangements of the complex. This is done by fitting the experimental collision cross-section values with in silico omega values calculated from generated model structures. On the whole, this field is still in its early years, and further development is required to make this approach generic and applicable to a wide range of complexes. Surface representation of the tetrameric form of bovine hemoglobin is shown here. The oxygen transporter hemoglobin complex can serve as an example for the approach mentioned above. Hemoglobin is a tetrameric protein complex composed of 2 alpha and 2 beta subunits, coloured blue and red respectively, which form a dimer of alpha-beta dimers. The IMMS spectrum of hemoglobin is shown here. The acquired IMMS spectrum of the complex reveals a major charge series distribution corresponding to the intact complex and minor charge series which fits the masses of the alpha-beta dimer and the alpha and beta monomeric subunits. The theoretical and measured CCS of the different forms of hemoglobin is shown here. Drift time values retrieved for several charge states of the dimeric and tetrameric forms were used to calculate the omega values. These were compared to the theoretical values. Given that a tetrameric complex has 3 possibilities of association, either cyclic, dihedral, or chain-like packings, by calculating the increase in omega when moving from a dimer to a tetramer, the structural organization can be predicted. Previous studies and our own experiments have shown strong correlation between measured CCSs and protein surface areas derived from crystal structure data. This correlation can be used to calculate the expected increase in surface area of a tetramer compared to a dimer for the different packing forms. This is done by considering each subunit as a spheric object. A chain-like assembly will increase the tetramer CCS at about twice, while a C4 or D2 packing will yield an increase of about 1.5 and 1.67 respectively. The calculated ratio between the measured CCS values of the tetrameric and dimeric forms of hemoglobin was 1.57 plus or minus 0.03. This number illustrates that the native structure is not linearly organized, but is arranged in a more compact form, either as a cyclic or dihedral tetramer. When repeating the same calculation on the resolved crystal structure of hemoglobin, the ratio of surface areas of tetrameric to dimeric forms was 1.63, which fits a D2 symmetry. Obviously, this geometric model is simplified, and protein subunits are not merely spherical. However, this calculation demonstrates the exciting potential IMMS holds for revealing the packing of complexes with unknown high-resolution structures.
We've just shown you how to measure the drift time of the protein and protein complexes and how to calculate their collision cross-section values.
When doing this procedure, it is important to acquire the IMMS data for the calibrant proteins using the exact same conditions used for the target protein or protein complexes.
Moreover, we strongly recommend repeating at least 3 times of these experiments and determine standard deviation of these triplicate measurements.
So that's it. Thank you for watching and good luck with your experiments.